This is our third lesson. This week we're going to finish chapter 2. We'll talk about autonomous equations and population dynamics, exact equations, and using substitutions to solve some differential equations. First, what is an autonomous equation? An autonomous equation is an equation which looks like dy dt is equal to some function of y. The key point here is that our function depends only on y. It's not a function of t. For the first example, I want to talk about cats living in Istanbul. Let yt denote the number of cats in Istanbul, and we want to model the change in y. The simplest model is just to assume that the rate of change of y is proportional to y. As we talked about last week, proportional means is equal to a constant multiplied by. So we're going to assume that dy dt is equal to some constant r multiplied by y. And we're going to be assuming that r is a positive number. We know how to solve this initial value problem. Y prime is equal to ry with an initial condition. From last week, we know how to solve this. It's a linear equation and it's a separable equation. And the solution is y is equal to the initial condition y0 multiplied by e to the rt. And the solution looks like this. Now, this model predicts that the number of cats in Istanbul will increase exponentially. This is a reasonable model if y is small, but as y gets bigger, it becomes unreasonable. It can't be true that the number of cats will always increase exponentially, because at some point something will happen to stop it. At some point the food will run out, there'll be no space left to fit any more cats in, people will get angry at the cats, etc., etc. Something will stop the number of cats increasing like this. So we need a better model for the number of cats in Istanbul. For our next model, we're going to replace the constant r by some function h of y. So we're going to be looking at dy dt is h of y multiplied by y. And we want to choose this function h, which satisfies three properties. For the previous model, we were happy with it for small y. So for small y, we want h of y to still be approximately equal to r. So for at least small y, the model will be the same as the previous one. The problem with the previous one was what happened when y got bigger and bigger. To fix this problem, we want a function h of y which decreases as y grows larger. And in fact, when y is very, very large, we want h of y to be a negative number. The simplest function like this is h of y is equal to r minus ay. The graph looks something like this. When y is small, the function is roughly equal to r. As y gets bigger, the function decreases, and if y is very, very large, the function is negative. So we're going to be looking at the differential equation. Dy dt is equal to r minus ay multiplied by y. And we're actually going to write this a slightly different way. We're going to write this as dy dt is equal to r multiplied by 1 minus y over k multiplied by y, for constants r and k, positive constants r and k. This equation is called the logistic equation. We're not going to solve this equation, but we're going to try to understand it. First, we're going to look for equilibrium solutions. An equilibrium solution is a solution where the derivative is always equal to 0. So we're going to start with dy dt is equal to 0, and we're going to put this into the equation. And then we're going to see, this means This implies that we must have y is equal to 0, or we must have y is equal to k. These equilibrium solutions are important. If we look at more solutions, and I'm going to show this to you on the next slide, we can see that the other solutions converge towards y is equal to k, but they diverge from y equal to 0. I want to investigate further. How can we understand the behavior of these other solutions without solving the equation? To be able to understand this, to be able to draw a graph like the previous graph without solving the equation, first thing I'm going to want to do is I'm going to want to graph dy dt against y. Remember, dy dt, our function, is r 1 minus y over k multiplied by y. If we plot this function against y, we have a curve which looks like this. When dy dt is greater than 0, that means y is increasing. When dy dt is less than 0, this means that y is decreasing. We can show this on the graph by drawing some green arrows. To show that the function is increasing, to show that y is getting bigger, I draw a green arrow pointing to the right. Where the function is negative, where y is getting smaller, where y is decreasing, I show this by drawing an arrow pointing to the left. To investigate further, we're going to look at the second derivative. We're going to look at d squared y dt squared. Now, go back to the more general case. If we start with the general autonomous equation, dy dt is equal to f of y, then the second derivative must be the derivative of this function. And by the chain rule, that's f prime dy dt. But of course, dy dt is just f. So we end up with f prime multiplied by f. The solution is going to be concave up when the second derivative is positive. Think back to first year calculus. So the second derivative is positive, that means concave up. And for an autonomous equation, we're going to have concave up when both f and f prime are positive, or we have concave up when they are both negative. Because positive multiplied by positive is positive, negative multiplied by negative is positive. And the solution is going to be concave down when the second derivative is negative. That occurs when one of these two functions, f and f prime, is positive and the other one is negative. Let's look again at the graph f equal to r 1 minus y over k, y against y. On the first part of the graph, where y is between 0 and k over 2, f is positive, so the function is increasing. F prime is positive because the function is getting bigger. Positive multiplied by positive is positive, so we have concave up. The solution will be increasing and concave up if y is between 0 and k over 2. The second part of the graph, here again the function is positive, but the function is decreasing, so f prime is negative. We can see here that the solution must be increasing and concave down. I'm not talking about the function f, I'm talking about the solution y. The solution y must be increasing and concave down. And then finally, the right part of the function. Here, f is a negative function and f is decreasing, so f prime is negative. Y is decreasing, but because we have negative multiplied by negative is positive, y must be concave up here. Moreover, we had a theorem from last week which said if we have a first order equation and all the functions are nice, then two solutions cannot intersect. They can get close together, but they can't cross. With this information, we can sketch some solutions. We have the green arrows from before. This tells us where the function is where the solution is increasing, where the solution is decreasing. And we've also done concave up and concave down. Between 0 and k over 2, the function is increasing and concave up. We can just sketch these. We don't need to solve the solution, we can just sketch these curves. Between k over 2 and k, the solution is increasing and concave down. So it must curve something like this. We already know the equilibrium solution k, and we know that solutions can't intersect, they can't cross over k. So all that can happen is they must be getting close to it. And in the top part, for y greater than k, solutions we've seen must be decreasing and concave up. They can't cross y equal to k, but so they must decrease but curve like this and get close to k. Because the solutions are converging towards y equal to k, they're getting close to y equal to k, we say that y equal to k is an asymptotically stable equilibrium solution. Or to say it another way, we can say y equal to k is an asymptotically stable critical point. Because the solutions are diverging or moving away from y equal to 0, we say that y equal to 0 is an unstable equilibrium solution, or to say it another way, is an unstable critical point. Equilibrium solutions we can classify like this. We can classify them by understanding the green arrows. If all of the green arrows are pointing towards an equilibrium solution, then the equilibrium solution must be asymptotically stable. Depending on our domain, we might only have one green arrow or we might have two green arrows. If they're all pointing towards, then we are asymptotically stable. If they're all pointing away from the equilibrium point, equilibrium solution or critical point, then this equilibrium solution or critical point is unstable. The third possibility, we might have one green arrow pointing towards it and one moving away. Then we say that the equilibrium solution is semi-stable. For example, find all of the critical points of dy dt is equal to y, 1 minus y squared. And you note, we're letting the initial condition, y0, be any number between minus infinity and infinity. So when we draw the graph of f of y against y, we're going to have to draw the whole y-axis. So find the critical points or the equilibrium solutions of this differential equation and classify each one as asymptotically stable, unstable, or semi-stable. First thing we do is we sketch the graph of f of y against y. As I said, because the initial point is between minus infinity and infinity, we're drawing the whole y-axis here, all of the way from minus infinity to infinity. When the function is positive, we draw a green arrow pointing to the right. When the function is negative, we draw a green arrow pointing to the left. And so on. Now I'm ready to answer the question. What are the equilibrium solutions? What are the critical points? There's one here at -1, there's one here at 0, and there's one here at 1. Classify each one as asymptotically stable, unstable, or semi-stable. We look at the green arrows. At -1, both arrows are pointing towards it, so this is asymptotically stable. At 0, the green arrows are pointing away, we are unstable. And at 1, green arrows are pointing towards, we're asymptotically stable. Another one. Find all of the critical points of dy dt is equal to y minus 2 squared, and classify each as asymptotically stable, unstable, or semi-stable. We do this the same way. First, we sketch f of y against y, and we draw our green arrows. What are the critical points? The critical points are the points where f prime is equal to 0. 0 and 2. Are they asymptotically stable, unstable, or semi-stable? At 0, the green arrows are moving away, so it must be unstable. At 2, there's one green arrow pointing towards 2 and one green arrow pointing away from 2. So y equal to 2 must be semi-stable. Next example. Consider the autonomous differential equation dy dt is equal to y to the power 4 minus 5y cubed plus 6y squared. Part 1. Find all of the critical points of this differential equation. Part 2. Sketch the graph of f of y versus y. Step 3. Determine whether each critical point is asymptotically stable, unstable, or semi-stable. And step 4, sketch 10 or more different solutions to this differential equation. This is actually an exam question which I asked way back in 2013 for a slightly different course. In 2013, I gave students 30 minutes to solve this question. So, part 1, find the critical points. To find the critical points, we need to factorize this function. We can write this as y squared, y minus 2, y minus 3. How do we get this equal to 0? This is 0 if y is 0. This is 0 if y is equal to 2, and this is 0 if y is equal to 3. So these are the critical points, 0, 2, and 3. Step 2, plot or graph f of y against y. Well, we know we must be 0 at 0, and at 2, and at 3. But does the curve curve up, or does it curve down? What happens, for example, if y is equal to 1? Then we get 1 squared minus 1 multiplied by minus 2. That's a positive number, so we must be somewhere up here. What about if we are, let's say, at 2.5? That's positive number multiplied by positive number multiplied by negative number. We're going to be somewhere down here. At 4, say, 4 squared multiplied by 2 multiplied by 1. That's a positive number, so we're up here. I'm just going to join these curves together. What about y is equal to minus 1? Y squared is positive, y minus 2 is negative, y minus 3 is negative. This is positive, so we're up here. So the graph, the very rough graph, should look something like this. Here's a better picture. And of course, we're going to want to add the green arrows here. Part 3, classify each one as asymptotically stable, unstable, or semi-stable. So, a question for you. Y equal to 0. Is this asymptotically stable, unstable, or semi-stable? Remember, we're looking at the green arrows. Are the green arrows both pointing towards y equal to 0? Are they both moving away? Or do we have one towards and one moving away?
So it's a semi-stable.
Both the arrows are pointing towards, then our critical point is stable. If they're both moving away, then it's unstable. If one is pointing towards it and one is pointing away, then the critical point is semi-stable. One person correctly wrote that this is semi-stable. What about y equal to 2? And finally, what about y equal to 3? Is y equal to 3 asymptotically stable, unstable, or semi-stable? Three people are correct. Y equal to 3 is unstable. And 10 people didn't give a response. Y equal to 0 is semi-stable because we have one arrow towards, one arrow away. Y equal to 2 is asymptotically stable because both the arrows are pointing towards 2. Y equal to 3 is unstable because both of the arrows are pointing away. And then the final part of this question is sketch some solutions to this differential equation. This is actually quite a difficult equation to solve, so I had to use a computer to generate these solutions. We have the critical points, the equilibrium solutions, y equal to 2, y equal to 3, and y equal to 0. Y equal to 0 is semi-stable. Solutions underneath it move towards y equal to 0, but solutions above it move away. Y is equal to 2 is stable. Solutions are moving towards it. Y equal to 3 is unstable. Solutions are moving away. If the students in 2013 sketched something like this, then they got the points. Let's go back to talking about cats in Istanbul. Now let's suppose we look at a different model. dy dt is minus r, 1 minus y over ty, where t is greater than 0 and r is greater than 0. This is not the logistic equation because now we have a minus in front. We can understand this in the same way. We can sketch f of y against y, and we can draw green arrows. And then from there, we can say that the equilibrium solutions are y equal to 0, which is asymptotically stable, y is equal to t is unstable. With this information, we can sketch some solutions. And they look like this. Depending on the initial condition, we either have that y tends to 0 or y tends to infinity, as t tends to infinity. The number t is called a threshold level. If we're underneath the threshold level, then no growth happens. The number of cats in Istanbul will decrease to 0. The population of some species does have a threshold property. What it means is if there's not enough of that individual in an area, then the species becomes extinct. There's a problem with this model. The problem is that, again, the model predicts that the number of cats in Istanbul will increase to infinity. So we need a more advanced model. Next, we're going to combine the two previous ideas. I want a logistic growth bit. That's the 1 minus y over k. And I want to include a threshold property. So I'm including a 1 minus y over t property. And just to make this right, and I'll leave this to you to think about having a minus sign at the front. And we're going to be assuming that k is a bigger positive number than t. We're going to be assuming that we have something like this. Y equal to 0 is asymptotically stable. Y equal to t is unstable. Y equal to k is asymptotically stable. And the solutions look something like this. And this is actually quite a good model for animals. This is an equation which has been used by biologists to model certain populations of animals. K is the typical population of the animals, if nothing interferes with it. T is the threshold property. If for some reason the number of animals is pushed below T, then the number of animals decreases, and the animal goes extinct. Our next topic for today is the topic of exact equations. Previously, we've looked at two special types of first-order equations. We've looked at linear equations and separable equations. We've looked at autonomous equations, but of course, an autonomous equation is also a separable equation. Now we're going to look at a third special type of equation, which is called an exact equation. To motivate this, let's start with the example 2x plus y squared plus 2xy, y prime is equal to 0. This equation is not linear. Why is it not linear? Because there's a y squared here, and there's also a y multiplied by y prime. And this equation is not separable. I'll leave this for you to check. It's not possible to move all of the x to one side of the equal sign and all of the y terms to the other side. So we need another method to solve this type of equation. Now note, if we know of a special function called psi, which is x squared plus xy squared, then the x partial derivative of this function is 2x plus y squared, and the y partial derivative is 2xy. So the equation we're looking at is really d psi dx plus d psi dy dx is equal to 0. And if you remember your chain rule, this left-hand side is the same as the x derivative of psi. So our differential equation is really just d dx of x squared plus xy squared is equal to 0. And of course, we know how to solve this. We integrate both sides to get x squared plus xy squared is equal to a constant. The key step was finding the special function psi. If we can find the special function psi, then the answer is just psi is equal to a constant. Now, let's go to a more general case. Consider m plus n, y prime is equal to 0. If we can find a function xi such that the x derivative of xi is equal to m and the y derivative of xi is equal to n, then equation 3 is called an exact equation. And the idea is, if we have an exact equation, then we can rearrange our equation to look like 0 is equal to the x derivative of xi, and then of course the solution to the differential equation is xi is equal to c. So this is our strategy. How do we solve an exact equation? Step 1, we need to find psi, and then step 2, we can just write the solution as xi is equal to c. We're going to be using lots of derivatives here, and I want to use a neater notation. If I write f prime, I mean an ordinary derivative. When I want partial derivatives, I'm going to use subscript. If I write something like f subscript x, that means the x partial derivative of f. And likewise, if I write f subscript y, that means the y partial derivative. Suppose we have some nice functions. Precisely, let's suppose m, n, my, and nx are continuous on a rectangle. Don't worry too much about that. That just says, let's suppose we have nice functions. Then we have a theorem which says the differential equation m plus ny prime equal to 0 is exact if and only if my is equal to nx. For example, Consider y cos x plus 2x e to the power y plus sine x plus x squared e to the power y minus 1, y prime is equal to 0. Is this equation exact? If the answer is yes, solve it. We need m and n, and then we're going to calculate the y partial derivative of m and the x partial derivative of n. If these are the same, then our equation is exact, and we know how to solve it. So first, we're going to take the y partial derivative of m. When we do partial derivatives, we pretend that the other variable is a constant. We ignore the other variable. So because we're differentiating with respect to y, we're going to ignore the cos x, just leave cos x as it is, and we're going to ignore 2y. We'll just leave that as it is. The derivative of y is 1, and the derivative of e to the y is just e to the y. So my must be cos x plus 2x e to the power y. Then we need to find the x partial derivative of n. Derivative of sine x, so that's cos x. The derivative of x squared, of course, is 2x. E to the power y, we just leave that as it is. When we're doing the x derivative, we just ignore the y's. We'll just leave this as it is. And the derivative of minus 1, of course, is 0. So again, we get cos x plus 2x e to the power y. And these are the same. My is equal to nx, so we have an exact equation. We want to solve this. Because it's exact, we know that there must exist a function xi such that the xi of x is equal to m and the xi of y is equal to n. We need to find this function xi. What we're going to do is we're going to pick one of these two equations, and it doesn't matter which one we pick. For this example, I'm going to pick the first one, but it really doesn't matter. We could start with the second one if we wanted to. I'm going to take the first equation and I'm going to integrate. I'm integrating with respect to. WRT is with respect to. So derivative of cos is sine. I get y sine x. So integral of 2x is x squared. So I get x squared e to the power y. And then normally when I integrate, I have plus a constant. But when we integrate with two variables, instead of plus c, it must be plus a function of the other variable. Because we're integrating with respect to x, it must be plus h of y on the end instead of plus c. And then we differentiate with respect to the other variable. Because I integrated with respect to x, now I'm differentiating with respect to the other variable, which is y. Derivative of y sine x is sine x. Derivative of x squared e to the power y is x squared e to the power y. And the derivative of h is h prime. Now look at what we have. Now I have two equations for y, for xi y. And these two must be the same. They both have sine x. They both have x squared e to the power y. One of them has plus h prime and the other one has minus 1. Because these equations must be the same, we must have that h prime is equal to minus 1. H prime is minus 1. We can choose any function h which satisfies this, so let's just choose h of y is equal to minus y. And then we're pretty much finished, because we can put that in here, and then we know xi. Xi must be y sine x plus x squared e to the power y minus y. And as soon as we know xi, we then know the solution, because the solution is always xi is equal to a constant. The solution to this differential equation is y sine x plus x squared e to the power y minus y is equal to c. Let's do another one. Consider y e to the power xy plus e to the power xy y prime is equal to 0. Is this differential equation exact? If the answer is yes, then solve it. If the answer is no, then we're finished. So we can write down m and n. We can do our partial derivatives, my and nx. And my is not the same as nx. So this differential equation is not exact. So that's the end of this question. Next one. Consider 4x cubed, y cubed plus 1 over x plus 3x to the power 4, y squared plus 1 over y prime is equal to 0. Is this equation exact? And if the answer is yes, solve it. This one I'm going to leave for you. If you're rewatching the video, pause it now and try to solve it yourself. You should be able to find that this equation is exact, and the solution is x to the power 4 y cubed plus natural logarithm of the absolute value of x plus natural logarithm of the absolute value of y is equal to c. I leave this for you to do. Another one. Consider 1 plus 2y plus 3y squared, y prime is equal to 0. Is this differential equation exact? And if the answer is yes, solve it. We write down m and n, we calculate my and nx, and yes, we find that they are the same. So this equation is exact. Because it's exact, there must exist a function xi such that xi of x is equal to m, which is 1, and xi of y is equal to n, 1 plus 2y plus 3y squared. We need to find xi, and then we'll write down the solution as xi is equal to a constant. Now we could start with either of these equations. It doesn't matter if we start with the first equation or we start with the second equation. I'm going to solve this twice. First, I'm going to start with the first equation, and then I'm going to repeat this solution and start with the second equation. And this time I'm not writing all of the details. This is not a perfect solution. This is not good enough to be an answer to the exam question. I'm just giving you the bare minimum here. I'm starting with the first equation, xi x is equal to 1, and I'm going to integrate this with respect to x to get xi is x plus h of y. Because I've integrated with respect to x, I differentiate with respect to the other variable. I differentiate with respect to y to get h prime of y. And that must be the same as 1 plus 2y plus 3y squared. So I must have that h prime is 1 plus 2y plus 3y squared. Integrate that. H we could take as y plus y squared plus y cubed. And therefore xi must be x plus y squared plus y cubed. Let's do this again, but let's start with the second equation. Let's suppose instead I start with xi y is 1 plus 2y plus 3y squared. This time I'm going to integrate with respect to y. Integrating with respect to y plus y squared plus y cubed. And because we're integrating with respect to y, instead of adding on a function of y, we must add on a function of x this time. I integrated with respect to y. Next, I differentiate with respect to the other variables. So now I'm differentiating with respect to x to get xi x is h prime of x. Look up to the top. That means h prime must be 1, h must be x, and therefore xi must be x plus y squared plus y cubed, which of course is exactly the same as the one we found using the other method. And then we can write down the solution. x plus y squared plus y cubed is equal to c. It doesn't matter which equation you start with, just choose one of them, integrate it, then differentiate it, and compare it with the other equation. Consider 3xy plus y squared plus x squared plus xy, y prime is equal to 0. Is this ordinary differential equation exact? If the answer is yes, solve it. We write down mn, my, and nx, and we see that nx is not the same as my. So this equation is not exact. So if we want to we can stop here. Our method will not work. But this time I'm not going to stop here. This time I'm going to try using our method, and I want to see what goes wrong. The method's not going to work, but why does it not work? What goes wrong? Let's try. So suppose that there does exist a function psi. We know that there doesn't exist a psi. We know that something's going to go wrong, but we're going to just suppose that in fact there does exist one. Pick one of these equations. Let's say we pick the first one, integrate it, and then differentiate it, and compare it with the other equation. We see that we want to have x squared plus xy is equal to 3 over 2x squared plus 2xy plus h prime of y. And rearranging this, we need to be able to find a function h which satisfies h prime is minus a half x squared and minus x squared. Now, this is not possible because on the left side there's only y. There's no x on the left, only y. And on the right side there's x and y. So this is not possible. H of y must be a function of y, but the right-hand side depends on both x and y. This means it's not possible to find h, and therefore it's not possible to find psi. Why did our method fail? Our method failed ultimately because my is not the same as nx. It is, however, possible to solve this equation. It's possible to solve this equation using integrating factors. Let me remind you, how did we solve linear equations? We found a special function called an integrating factor, and we multiplied by the equation by the integrating factor, and it made the equation easier. We're going to do the same type of thing here. We're going to take our equation, which is not exact, and we're going to multiply it by a special function called an integrating factor, which will turn it into an exact equation. The general case, consider m dx plus n dy is equal to 0. And I want to suppose that equation 4 is not exact. Let's suppose we multiply this by some unknown function, mu x, of x and y. Then we get a new equation. And this new equation is exact if and only if the y derivative of mu multiplied by m is the same as the x derivative of mu multiplied by n. Now, let's start with this. Let's start with mu my is equal to mu nx. Use the product rule. That's the same as mu y m plus mu m y is equal to mu x n plus mu nx. And rearrange that slightly. M mu y minus n mu x plus my minus nx, mu is equal to 0. If we can find an integrating factor mu of x and y which solves equation 6, then equation 5 is exact, and we know how to solve exact equations. But equation 6 is a first-order partial differential equation, and PDEs are typically not easy to solve. Instead of trying to make this easier for ourselves, we've ended up making this more difficult. Instead of having an ODE to solve, we've left ourselves with a partial differential equation to solve. How can we make this easier? Instead of looking for an integrating factor mu of x and y, instead we might hope to find an integrating factor which only depends on x. If mu only depends on x, then mu y is going to be equal to 0, and equation 6 becomes easier. It becomes 0 minus n d mu dx plus my minus nx mu is equal to 0, which we can rearrange to d mu dx is equal to my minus nx divided by n multiplied by mu. If we can find a function mu of x which solves this differential equation, then we have our integrating factor. We can multiply it by our differential equation to change our differential equation into an exact equation, and then we can solve it. If my minus nx over n is a function only of x, then there exists an integrating factor. If my minus nx over n is a function of both x and y, then we can't do this. We just know equation 7 is both linear and separable. So if my minus nx over n is a function only of x, then you know two ways to solve equation 7. Instead, we might have started by looking for mu y, and then we would have a similar equation. We just pop back. In this one, there's an n on the bottom, and it's my first. This one, we have m on the bottom instead of n, and we've swapped the positions of nx and my. If this was a classroom course, and if you were having exams in a classroom, then we would be expecting you to memorize equations 7 and 8. Your exams will be online. I suggest you have equation 7 and equation 8 written down on a piece of paper next to you before you start an exam. For example, the equation I looked at before, solve 3xy plus y squared plus x squared plus xyy prime is equal to 0. We know that this equation is not exact, so we're going to try to find an integrating factor. We need mn, my, and nx. And then we're going to calculate my minus nx over n and nx minus my over m. And we're going to hope that either the first one is a function only of x or the second one is a function only of y. Substitute everything in, simplify. The first one becomes 1 divided by x, and the second one becomes this complicated thing. The first one is the one we want. 1 divided by x is a function only of x, so this is the one we're going to use. Second one is a function of both x and y. We can't use the second one. Because my minus nan is a function only of x, it's going to be possible to find an integrating factor mu of x. Because nx minus my over m is not a function only of y, it's not possible to find mu of y. So let's do the calculation. Solve d mu dx is my minus nx over n mu. In other words, solve d mu dx is equal to mu divided by x. This is linear and this is separable. I choose to solve this as a separable equation. I'm moving all of the mu terms to the left, all of the x terms to the right. Because I've separated the variables, I'm allowed to integrate. And after rearranging, I get mu is equal to cx. We only need to find one integrating factor. We don't need every single integrating factor. We just need to find one integrating factor which works. So we can choose whichever c that we want, and because I like easy functions, I'm going to choose c equals 1. So the integrating factor that I want is mu is equal to x. So what do? We take our original equation and we multiply it by x. Instead of 3xy, we get 3x squared y. Instead of y squared, we get xy squared. Instead of x squared, we get x cubed. Instead of xy, we get x squared y. If we've not made any mistakes, then this should be an exact equation. Now I'm going to call this m, and I'm going to call this n. That's the new m and new n, but let's just call it m and n. I'll leave it for you to check that my is 3x squared plus 2xy, and that's the same as mx. So this is an exact equation. We know how to solve exact equations. We need to find a function xi such that xi x is this first function and xi y is this second function. Choose one of these, it doesn't matter which one. I'm going to choose the first one again. Integrate it with respect to x. I'm going to go quickly here. And then differentiate it with respect to y and compare the function we've just found with the function that we've started with. X cubed plus x squared y must be the same as x cubed plus x squared y plus h prime of y. We can choose any function h that we want which satisfies this. So we can choose an easiest one that we want. We can choose h of y is equal to 0 if we want. So if this is 0, xi must be just x cubed y plus a half x squared y squared. And as soon as we know xi, we know the solution. The solution to the differential equation, that's the differential equation we started with, as well as the differential equation multiplied by x, must just be xi is equal to c. One more example. Solve y e to the power xy plus 2 over y plus x e to the power xy, y prime is equal to 0. I'll leave it for you to check that this differential equation is not exact. And I'm going to leave it for you to check that my minus nx over n is minus 2 over y plus x. This is not what we want. This is x, both have x and y here. We don't want this. Nx minus my over m is 2 over y. This is a function only of y. This is the one we want. Because this is a function only of y, we're going to find an integrating factor mu of y. We need to solve d mu dy is 2 over y mu. And I leave this for you. I'm not going to bother doing this. You know how to solve this. I'll leave it for you to check that the solution is y squared. We take our differential equation and we multiply it by y squared. And then, again, I'm not going to do this. I'll leave this for you to complete. If you're rewatching it, pause the video here, fill in this calculation and check that the answer to this problem is y squared e to the power xy is equal to a constant. And that just leaves section 2.6, which is about substitutions. Today we're going to have a long lesson. Some of my lessons are going to be longer than other ones. Today we're going to go over an hour. When we get to the end of term, when we get to the more difficult thing, I've put less stuff in. So at the end of term, the lessons are going to be less than 60 minutes long. Before I start the last section, I'm going to take a 10-minute break. Our final topic for today is the topic of substitutions. Let me just remind you, how do we calculate an integral such as 3x squared sine x cubed dx? We use a substitution to turn this into an easier integral. In this case, we use u is equal to x cubed, and we turn our slightly difficult integral into the easy integral of sine u du. We can use a similar idea for differential equations. Sometimes we can use the same idea to solve differential equations. Let's suppose we have some difficult differential equation that we want to solve. Sometimes we can do a substitution. We're going to use the notation v is equal to a function of x and y to turn our difficult equation into an easy equation. If it's an easy equation, then we can solve it to find v. After we know v, we do our substitution again to find the function y that we really want. That's the idea in this section. In this course, we're going to use substitutions to solve two types of first-order differential equations: homogeneous equations and Bernoulli equations. First, homogeneous equations. A homogeneous equation is an equation that we can rearrange so that it looks like dy dx is equal to some function of y divided by x. It's always y divided by x. So some examples. Dy dx is equal to cos y divided by x, a function of y divided by x. Or dy dx is cos x divided by y. Again, this is a function of y divided by x. Or dy dx is y over x cubed plus y over x. Or dy dx is y over x minus 4, 1 minus y over x. These are all functions of the form dy dx is equal to some function of y divided by x. And for a homogeneous equation, we always use the substitution v is equal to y divided by x. Or equivalently, we could write this as y is equal to x multiplied by vx. And then, using the product rule, dy dx must be the same as v plus x dv dx. And that's the two equations that we're going to be using. We're going to replace every v by y divided by x, and we're going to replace every dy dx by v plus x dv dx. For example, solve dy dx is equal to y minus 4x divided by x minus y. Note first that if we divide through by x, we get on the right-hand side y over x minus 4, 1 minus y over x. This is a function of y over x. This is a homogeneous equation. We're going to replace every y over x by v. So we have dy dx, I haven't changed this yet, is equal to v minus 4 divided by 1 minus v. We also have an equation for dy dx. We're going to be replacing dy dx by v plus x dv dx. So our equation becomes v plus x dv dx is equal to v minus 4, 1 minus v. And we can simplify this a little bit. We can take the v to the right-hand side, and put everything over 1 minus v, and we end up with v squared minus 4 divided by 1 minus v. Now note, this is a separable equation. X dv dx is equal to v squared minus 4 over 1 minus v is a separable equation. By doing our substitution, we've changed our more difficult equation into a separable equation. And we know how to solve separable equations. I'm going to solve it now, but I'm going to go quite quickly. This should be revision for you. What I do is I rearrange this to move all of the v terms to the left and all of the x terms to the right. And then I use partial fractions to write the left-hand side as minus 3 over 4 v plus 2 minus 1 over 4 v minus 2. And then I'm ready to integrate. Integrating, and I leave this v to check, and then rearranging, I end up with absolute value of vx plus 2x cubed plus absolute value of vx minus 2x is equal to c. I leave this v to check. Now that we have an equation for v, there's only one more thing to do. We need to make a substitution again, and we need to get an equation for y. If we replace every vx by y, then we find the solution that we want. Absolute value of absolute value of y plus 2x cubed, absolute value of y minus 2x is equal to c. So to recap, what do we do to solve a homogeneous equation? We always use the substitution v is equal to y divided by x. And then the second equation we use, which we get by differentiating the first one, dy dx is equal to v plus x dv dx. After we've put these in, we have a separable equation. We solve the separable equation to find v, and then we do the substitution again to find y. I have another example to show you. Solve dy dx is equal to x squared plus 3y squared divided by 2xy. First, we rearrange it, divide everything by x squared, and we see that we now have a function of y divided by x. We can do our substitutions. We can replace every y over x by v. The right-hand side becomes 1 plus 3v squared divided by 2v. And we replace dy dx by v plus x dv dx. The left side, which is always the same, becomes v plus x dv dx, always the same on the left. Let's rearrange this a little bit. Take the v to the right side by doing minus v on both sides. Put everything over 2v and simplify, and the right side becomes 1 plus v squared over 2v. This is a separable differential equation. You know how to solve this. I've written a mini solution here. Again, this is not a perfect exam solution because it doesn't have all the details. It's just enough to see that the answer is 1 plus v squared minus cx is equal to 0. One final step to do before we're finished. We need to substitute back in to get an equation for y. I'm going to replace every v by y over x to get this, and then rearrange it just slightly to get a neat solution. X squared plus y squared minus cx cubed is equal to 0. And I'm going to leave it like this. The second type of equation that we can use substitutions for is Bernoulli equations. An equation which looks like y prime plus pt of y is equal to qt y to the power n is called a Bernoulli equation. When we try to solve Bernoulli equations, again, we can use a substitution. And the substitution that we always use is v of x is equal to y to the power 1 minus n. Whatever number we have here, whatever the power of y is, we do the substitution v is equal to y to the power 1 minus this number. So for example, solve dy dx minus 3 over 2xy is equal to 2x y to the power minus 1. This is a Bernoulli equation where here we have n is equal to minus 1. So the substitution we're going to use is v is equal to y to the power 1 minus n. 1 minus minus 1 is 2. We're going to use the substitution v is equal to y squared. If v is y squared, then that means y is equal to v to the power of a half. And by the chain rule, dy dx is the same as dy dv, dv dx, or a half v to the power minus a half dv dx. These are the two equations we're going to use. These are the two substitutions we're going to use. Every time we see a y, we're going to replace this by v to the power of a half, and we're going to replace dy dx by a half v to the power minus a half dv dx. So here we go. Put these substitutions in, and we get a half v to the power minus a half dv dx minus 3 over 2x v to the power of a half is equal to 2x v to the power minus a half. Doesn't look like it yet, but this is an easier equation than the one we started with. We're just going to simplify this a little bit. What we can do is we're just going to multiply by 2 to the power 2 multiplied by v to the power of a half, and look, we have a nice simple equation. dv dx minus 3 over xv is equal to 4x. And this is a linear equation. By doing our substitution, we've changed our difficult Bernoulli equation into a linear equation. You know how to solve linear equations. I'm going to solve it now. This next calculation should be revision for you. What we do is we use an integrating factor. Because we have minus 3 over x here, our integrating factor should be e to the power integral of minus 3 over x dx. And you can check that that's the same as x to the power minus 3. So we take our differential equation, and we're going to multiply this by x to the power minus 3. And what we get is x to the power minus 3 dv dx minus 3x to the power minus 4, v is equal to 4 x to the power minus 2. The left side, using the product rule, is just the same as the derivative of x to the power minus 3v. So we can integrate. Integrating gives x to the power minus 3v is minus 4x to the power minus 1 plus a constant. Multiply by x cubed to get v is minus 4x squared plus cx cubed. And then we're almost finished. Now that we know v, we can do our substitution and we can find y. Because of course, v is equal to y squared. So all I do is I take this v and I replace it by y squared to get the solution. Let me recap. To solve a Bernoulli equation, we do a substitution. We do the substitution v is equal to y to the power 1 minus n. Step 2, we solve a linear equation. And then step 3, we do our substitution again to find an equation for y. Final example of today's lesson. Solve x dy dx plus 6y is equal to 3xy to the power 4 over 3. This is a Bernoulli equation, and now n is 4 over 3. So we want v is equal to y to the power 1 minus n, or y to the power minus a third. That's the same as saying we want to use y is equal to v to the power minus 3. If y is v to the power minus 3, then by the chain rule, dy dx must be minus 3 v to the power minus 4 dv dx. Okay, that's what we needed to start with. Now we can substitute this into the differential equation. Substitute it in, simplify a little bit, and we end up with the linear equation dv dx minus 2 over xv is equal to minus 1. We know how to solve this. We used integrating factor x to the power minus 2. And I'll leave this for you to check. I won't go through the details. You can check that we find v is equal to x plus some constant x squared. All that's left to do is to substitute in v is equal to y to the power minus 1/3, and we get our solution. Rearrange a little bit. I'll leave this for you to check. Y is equal to 1 divided by x plus cx squared, all cubed. And that's the end of today's lesson. Next time, which is in 2 weeks' time, we'll start talking about chapter 3. Tomorrow is a national holiday. There's no lesson tomorrow. Next week is a religious holiday, so no lessons next week. I will see you again in 2 weeks' time. Are there any more questions?